All right, so cellular respiration, why do we do it? Well, it's basically a change machine. So if we have $10, $10 bill, but you want to get some snacks out of the snack machine, some pretzels or something, and the snack machine only takes quarters, it's really tough to walk around with a $10 bill and find someone who has 40 quarters in change. It's a lot easier to take it step by step by step, and that's what cellular respiration does. So here's the cell here, and here's $10 worth of glucose. And if we have insulin that is present and functioning, insulin will help glucose enter the cell. So now we have sugar inside the cell, C6H12O6. The first step is glycolysis. We're going to split that glucose in half, and we're going to form two pyruvic acids. That does not require oxygen, so we call that anaerobic. This is an anaerobic reaction, okay? So first step is splitting glucose in half. Next, if we have oxygen present outside the cell, oxygen will diffuse into the cell from a high concentration to a low concentration through simple diffusion, and the oxygen and the pyruvic acids will interact with the mitochondria, and the mitochondria will then, there are two series of reactions that happen within the mitochondria, Krebs cycle and electron transport chain, and the end result, after putting in $10 worth of glucose and oxygen, is we produce CO2, water, and 38 ATP. So ATP is equivalent to quarters. We can now use that ATP to do stuff within the cell, so it's a form of energy. Okay, but this requires oxygen. If we don't have oxygen, we cannot do that. We are stuck doing what we call anaerobic reactions. If we do have oxygen, we can then do aerobic reactions here, okay? And if we're stuck just doing the anaerobic because we don't have enough oxygen or we have no oxygen, those pyruvic acids get fermented to lactic acid. And we get 2 ATP as a result of this stuff going on here. So basically, you're putting in $10 worth of glucose and you're only getting 2 ATP if you don't have enough oxygen. So that's not really the best case scenario. Plus, lactic acid builds up. Well, lactic acid building up, we need to go over here and figure out what's going on too. So the more cellular respiration you do, right? The more cellular respiration, you're going to produce a lot of CO2. The more CO2 you produce, what it does is it combines with water to form carbonic acid, H2CO3. That carbonic acid will then dissociate to form bicarbonate, HCO3 minus, and H pluses. Well, so this means the more cellular respiration we do, the more CO2 builds up in your tissues, the more H pluses there are in your tissues. If you remember from pH, 0 is highly acidic, 14 is highly basic. So basically we've got pure H pluses over here, pure H minuses, OH minuses over here, rather. So if H pluses, these protons are building up in your bloodstream and in your tissues, that means we are driving your pH down closer to 0, and the arterial pH of your blood should be between 7.35 to 7.45. The problem is, when we change this, when we go either way, too high or too low, in this case, if we don't get rid of these H pluses by exhaling CO2, if we don't get rid of that CO2, we are then going to make our blood more acidic, which will then start to denature our proteins, and that is not good.